It's a pleasure to introduce the next speaker, Pietro Sternai, one of the leaders of the Topo Europe program, and he will speak on the interplay between geology and climate, and with an emphasis on the slow breath of Earth's living machine. So Pietro, floor is yours.
Thank you very much, Sid. Thank you everybody for inviting me. It's always a pleasure to discuss these problems with friends and colleagues. The contribution I can give here is bringing you back to long-term climate changes. So not the climate changes that we usually hear about from the news, but really how the long-term climate has evolved through time, also in response to the geodynamic forcing and what are the effects on the topography and life. So this figure on the left was shown already, is a sketch that I drew together with Sirt a few years ago now. It gives a sense of the complexity of the system, which we have discussed much about already, so I won't go into the details again. And it's always a temptation to give it up and say it's too complicated, let's simplify the entire system with sketches, but I see this as a challenge actually. So we've been discussing about the development and evolution of intelligent life, and I see this is as a challenge to become even more intelligent and try to disentangle the maze of interactions that each one of the arrows on the left or each one of the colors on the right really represent in the Earth system. So this is a major challenge. Of course, I won't discuss all of these arrows and colors. I just want to highlight a small number of them and discuss a little bit of the research that I'm doing together with lots of people on the topic. So in the first part, I'd like to discuss briefly what was the geodynamic forcing on climate throughout the Cenozoic. And for those of you who may not be familiar with the geological timescales, the Cenozoic is the last 65-ish million years, which is a relatively long term timescales for geology. It's not very long, but becoming long. And it's a good timescale and time window because the geological record is there. We have lots of data that we can use to understand how the system works. It's a long-term timescale to see the evolution of the system, but it's not too long that then the data becomes too sparse and it's difficult then to get the information we require. I also want to discuss briefly how we can use the geological record to constrain the fluxes of CO2 from the solid Earth into the surface reservoirs and out of the surface reservoirs. And this is fundamental if we want to really understand how the system works and what are the responsible mechanisms for the flow of carbon and carbon dioxide throughout the Earth system. And then, of course, we know that climate is not just about CO2. There is much more in it. But I particularly want to highlight an aspect that was not studied so far, maybe was not even realized so clearly so far. And this is a direct control on climate from the mantle dynamics, so the deeper layers of the Earth. So, we have the geological record, and we've got a pretty good understanding of how the Earth looked like and how is it composed and what is it made of on the present day. But thanks to the geological record and the seismological data that we have, we can also reconstruct how, with a relatively good degree of detail, how it evolves through time, throughout the Cenozoic, throughout the last 65 million years. And so you see here one proposed model upon which many of us overall, maybe not on the details, but overall agree. So the reddish and bluish blobs in the right-hand side of the plot have been discussed already as the material that wants to sink down, heavy and cold, and the reddish material is the material that is light, warm, and it wants to come up. And this is essentially mantle convection, okay? Is an effect of the thermal relaxation of the planet, which is the main engine for plate tectonics, for the motion of the continents on top of the Earth. Overall, throughout the Cenozoic, this engine has led to the northward motion of Africa, and you may see bits and pieces of continents detaching from the main body of Africa and drifting northward to collide into the southernmost margin of the Eurasian plate. Now, this northward motion has been driven essentially by the subduction, so the closure of the Neothethian Ocean, which you can see from the beginning of the movie here, was making a link from the Indian Ocean to the far right to the Atlantic Ocean in the left side of the plot. Now, the closure of this ocean, of course, had a major climatic effect, okay, because of ocean circulation, atmospheric circulation, and this climatic effect could also be retrieved. You see them on the left-hand side from the geological record, mostly from the sedimentological record. Okay, we've got climate proxy data that enable us to reconstruct how climate has evolved through time during this continental drifting and plate tectonic evolution. And you see, you can recognize essentially two time windows, the 60, 50-ish time windows where climate is relatively warm and even warming up until 50, and then from 50 on, climate has been cooling unsteadily, leading to glaciations and most recent late Pleistocene glacial interglacial cycles. Now, these long-term climate changes are essentially related to plate tectonics and mantle convection underneath. And the way we like to interpret these climate trends is by means of the geological carbon cycle, which was already mentioned. Essentially, the geological carbon cycle is responsible for the changes in the amount of carbon at the surface, and the amount of carbon at the surface drives long-term climate changes. This happens, or we like to simplify the system with two relatively simple chemical reactions that you see down there. They're simple enough that even I can understand and do the stoichiometry. The main player here are the weathering of silicate minerals, okay, which add up to CO2 and water from the surface reservoir, atmosphere and oceans, to generate calcium carbonate and other compounds that are then brought into the sedimentary basins and into subduction back into the mantle. And this is the main sink term in the carbon dioxide at the surface. The main source term is the recycling that occurs down in subduction zones, not only, but mostly in subduction zones. So C is very incompatible. It wants to come up again with melts and fluids. It interacts with the rocks on the way up to the surface, and eventually it's emitted in forms of CO2 and other carbon-bearing compounds from magmatic arcs. That's the source term in the geological carbon cycle. So the balance between these two major players essentially drives the changes in CO2 and associated changes in temperature throughout the Cenozoic. This is how we understand this. Because of the geodynamic history of the Cenozoic that I showed earlier, so the closure of the Neothethian Ocean and the collision of Indian plate, Arabian plate, Adria plate with the south margin of Eurasia, we have built up the so-called alpine Himalayan orogenic belt, okay? Which means we have uplifted the topography, and uplift of the topography implies erosion. Erosion implies the exhumation of new silicate minerals, and silicate minerals at the surface get weathered, and this, of course, drives the reduction of atmospheric CO2 content through the geological carbon cycle. So a big chunk of research has been done over the recent decades in trying to relate what we think is one of the major geodynamic events throughout the Cenozoic, so the collision between India and Arabia and Eurasia, and the uplift of the Himalayan and alpine Himalayan belt, and climate, essentially through the lens of the weathering term. Okay, so we know India started colliding into Eurasia around 50 million years ago, which it shouldn't be a coincidence that climate started cooling at that time. So most of the interpretation has been done in the sense uplift of the Himalayas, more erosion, more weathering, less CO2 into the atmosphere, and therefore climate cools down. Now we know the story is more complicated than this because we don't have a full explanation for the climate changes throughout the geodynamic history. So I was lucky enough to get funded from the ERC on a project that actually tries to tackles the problem from the other perspective, from the magmatic perspective. Okay, so we will be studying magmatic sedimentary rocks along the Neothethian and Alpine Himalayan belt to try see if we can reconcile the magmatic history and the climatic history throughout the Cenozoic. And I'm lucky enough to be able to show some preliminary results. The project has not started yet, but we did some research earlier on. So we sampled magmatic rocks and sedimentary rocks, although I'm not talking about sedimentary rocks now, magmatic rocks from 3 case studies along the Neothethian margin in Iran, in Ladakh, northwestern India, and southern Tibet. And these rocks are dated, relatively well dated. So we know we are, let's say, analyzing samples that were emplaced or erupted at the right time to tackle questions related to climate changes. And what we do on these rocks is to analyze the petrology, of course, but especially we measure the amount of volatiles within melt inclusions. Melt inclusions are droplets of magmas, essentially, that are trapped within phenocrysts in these rocks. And this is the only way to get direct constraints on the volatile content of these magmas, which is a proxy for the amount of CO2, if you want, that was released during the eruption of these rocks, okay? So we've done a few measurements on the Iranian samples, and you see a plot here where I show the CO2 content in these melt inclusions from some of these samples. We just got lucky, but the first samples we analyzed, they provided values that are much higher than common CO2 content from subduction zones. So this is a good hint that we are on a good path to get good constraints for past CO2 emissions and maybe climatic effects when these magmatic rocks were emplaced. And the age of these samples is around 40, which is coincidence with the Middle Eocene climate optimum, MECO, so that little wiggle that you see on the climate curve. And if you do some educated guess using the numbers that you can derive from melt inclusions, you can actually quantify the amount of CO2 released when those rocks were emplaced. And you can use climate models to show that the amount of these CO2 emissions is large enough to impact climate in a way that is consistent with the Middle Eocene climate optimum. So this is just the beginning, and there will be much more analysis and much more integrated work on this as the project moves on. But I'm pretty excited to show these preliminary results now. Another way of tackling the geological carbon cycle, as I mentioned earlier, is to try constrain the fluxes. Because in fact, these curves there give the overall amount of CO2 within the atmosphere, okay, or the surface reservoir, let's say. But this is not enough to pinpoint underlying mechanism. Ideally, as a geologist who's interested in the dynamic behavior of the entire system, you want to have fluxes because this is an additional information to pinpoint mechanisms. It's a bit like knowing the amount of water in the glass through time, but you don't know how much water is coming in and how much water is coming out. You want to know that to highlight processes. Over the last 3 years or so, with a very promising and motivated PhD student, Luca Castrogiovanni, we've been developing an algorithm which is essentially based on the same theory that seismologists use to derive information from seismic waves in terms of temperature or density anomalies. So they essentially get a seismic wave, and they parameterize the forward model in terms of temperature and density changes at depth. We do exactly the same thing, except that our seismic wave is the paleoclimate record, and our forward model is a very simple formulation of the geological carbon cycle. In fact, the simplest formulation that we could envisage of the geological carbon cycle, where the variation of CO2 at the surface through time is given by a source term minus a sink term, which depends on the temperatures, because we are really clear about the fact that weathering rates depends on the surface temperature. So I'm skipping the methodological details for the sake of time, but in fact we are not doing anything particularly fancy. We are applying an established technique to a different problem, let's say. And we can use different inversion schemes. Particularly, we use a reversible jump Markov chain Monte Carlo inverse scheme to parameterize the equation in terms of the gamma term and the beta t term in time, okay? So I'm jumping to the results here. On the top plot, you see the data that we used in terms of temperature, which is a leading term in the equation, and in terms of CO2 and the CO2 variations in time. The derivative is used for the left-hand side of the equation here. On the second plot, red and black curves show how well the algorithm is able to match the data. And the blue bars, which we call functions, give a sense of how much the variation of carbon in time and the temperature term are decoupled. What does that mean? It means that the algorithm needs to change either the gamma or the beta term in order to match the dc over dt when you've got high number of functions, okay? And if you don't have a high number of functions, that means that the variation in t can explain the variation in c, okay? So this is important because it's already giving an information on the underlying mechanism. We are saying those climate changes that are associated to a high number of functions must come from processes that are not directly dependent on temperature. What does that mean? The way I like to see it is that they may be related to volcanic outgassing, for instance, or generally speaking, not temperature-dependent processes such as albedo effect, orbital effects, or anything you can think of. There must be some things related or internal to the Earth system, let's say. And in the bottom two plots, you see the reconstructed gamma history, source CO2 fluxes, and sink CO2 fluxes. And this is what I believe is a true game changer in the study of the geological carbon cycles, because, for instance, most climate and paleoclimate models that was done so far essentially assume a constant source CO2 emission rate, and they assess climate just based on the paleogeography or paleotopography, whereas here we can also account for the solid earth outgassing or anything that you can think of could contribute to the source term. And the same for the weathering rates, if you want to think of the sink term as a weathering rate in time. And you may see also there are leading lag relationships that one can explore to really try understand the behavior of the Earth system, essentially. Now, this is very recent result. We are still building on this, but I like to see this as a good results that we can provide to the community of paleoclimate or any other community that is interested in the geological carbon cycle, including biologists, because this is a major outcome. Last but not least, beyond CO2, of course, as I said, climate is also related to other factors, and one factor that I believe was not enough considered was the mantle dynamics. Mantle dynamics drive plate tectonics, so continental drift and topographic evolution, but topographic evolution also in terms of dynamic topography versus isostatic topography. What does that mean? Essentially, the topography that we see out there, everywhere in the world, is the result of two components. One isostatic component, which is related to the thickness of the buoyant layer of the lithosphere, the crust, okay? You can think this like an iceberg floating on water. Water is denser than ice, and therefore ice sticks out of the water to some extent because of the density difference. But then there is another component in the observed topography, and this is related to the stresses that the convection in the underlying mantles is applying to the lithosphere. So when the mantle is uprising, the stresses are upward, and this is strong enough to uplift the topography to some extent. And when the mantle convection is driving downward flow, stresses are strong enough to suck the topography down and decrease the overall elevation. This is called dynamic topography, okay? And dynamic topography, it's been estimated many times from tectonicists and geologists. There is lots of debates on the magnitude of dynamic topography, especially at the local scale. But on a global scale, there is a relatively good agreement that it may vary in the order of 1, maybe 2 extreme, but 2 kilometers. And you've got major features in the East African Rift System, the American Cordilleras, Himalayan mountains and Tibetan Plateau also stick out, Australia. So there are major features that we are relatively well established. Now, my question was, how much does this topography influence the present-day climate? And I tackled the question collaborating with climatologists. I was not able to do that myself alone. So they suggested to use a general circulation model of intermediate complexity that tackles atmosphere dynamics. So we are dropping ocean dynamics for the moment. We would just want to tackle the first order questions on the continents. So we use this model, but we input not the observed topography as they usually do, but the isostatic topography. So we removed from the observed topography the dynamic component to see what was the effect of mantle dynamics on the present-day climate, okay? These are, so in the bottom plots you see the results in terms of temperature changes when you've got isostatic topography versus observed topographies on the climate models, and in terms of annual precipitation. So you see major changes. These are very first-order features, but very non-negligible features. Up to 100% precipitation change all around Africa, for instance. But also at higher latitudes, where precipitation are less important, you see major changes in the overall pattern, okay? And of course, there are changes also in terms of wind directions and magnitudes, and several other parameters that I don't even have the time to show here. But the point here that I want to make is that this is relevant features for human societies. The wind pattern, for instance, controls our flight schedule, birds' migration directions and timing, okay? So this is really relevant and very fundamental for the entire biosphere and for our society as well. So we should spend some time and understand this direct forcing on the mantle more carefully, because it's important for the Earth system. When I got these results and discussed this result with the climatologist I was working with, they say, okay, but we don't learn anything new about climate. And I said, well, maybe we don't, but we do understand something more about the Earth system, because we were not aware of a direct mantle contribution on the present-day climate, for instance. And now it looks like, or at least these model results look like they really suggest that there is a significant one. And since we have plate kinematic reconstructions and tectonic models at the timescales of the Cenozoic, very reliable models, we can also run the same exercise back in time and see how was the impact of mantle convection on paleoclimate, and therefore on life evolution, speciation, biodiversity, and so on. So this is really a new research frontier that I expect will be gaining attention in the future. So, leaving you with, for conclusion, plate tectonics drives long-term element cycling and topographic changes, and therefore it affects the evolution of climate and life. it's important to realize that there are relatively short-term forcing that entails very long-term effects, okay? And I've been discussing the closure of an ocean, for instance, which is of course a long-term process, but in fact the moment you close the ocean is relatively short, okay? Because you can narrow the ocean, but then at a given time you cut the connection and you change massively the ocean dynamics, for instance, and this entails very long-term effects on the climate, on the landscape, and therefore on life. And these, we must learn to shift timescales if we want to tackle biogeodynamical questions, as Taras also showed. We've got a new quantification of source and sink CO2 fluxes, which I believe is an important achievement for these sort of studies. And we also realize more and more about how tight is the coupling between the surface and the deep earth, especially when we consider this mantle dynamics contribution to climate. And as a take-home message, Taras was very good in giving this message already. The past is key to present day and future. And again, let's force ourselves to change timescales and space scale continuously, because otherwise there is no biogeodynamics research. Thank you.
Thanks a lot, Pietro, for a very clear and inspiring presentation. I am confident that Marta Becchesi will come back to the issue of CO2 fluids from greater depths later in the afternoon. For the sake of time, I would like to ask whether we have one question or comment from the floor. Yes, Taras, please.
Thank you very much, Pietro. What you have shown with these CO2 outfluxes from volcanic arc seems very important. Can you relate these, directly estimated volcanic fluxes to any, say, measurable parameters from plate reconstruction, like plate convergence rate or like plate topography or anything that can be used by people to project this result back in time or forward in time?
Yeah.
Thank you.
So this is actually one of the tasks of the ERC project. So I expect I will be able to do this in a few years' time. What I can say now is that the numbers match from the CO2 outflux inversion results and the numbers that we got from the actual analysis of magmatic rocks. And this was already a success. I was not expecting to be that lucky, but numbers match so far, so I believe we are on a good track to that. Yeah.
Pietro, ERC is financing high-risk, high-gain projects, and maybe we can come back to this high-risk issue later on in the day when we close the session with a discussion on challenges and opportunities. Yes. Yeah? Okay, thanks in advance. We move into the final presentation.